Hello, everyone. My name is Parker Smith. I am a senior at the Math, Science, and Technology Center at Paul Laurence Dunbar High School. And under the mentorship of Dr. Jeremy Van Cleve, I've been conducting research at the University of Kentucky. The title of my research project is Investigating the Impact of Inheritance Patterns on Cooperative Behavior in Graphs. So I did want to take a second to thank you all for tuning in to watch this. My guess is that it's in no way obligatory, but I do appreciate you taking the time out of your day to come and see the work that I've been doing. Now, just a brief overview of what this presentation is going to look like. It's going to be pretty basic. It'll be comparable to the other symposium presentations that you'll have seen. First, we're going to talk about some basic concepts that are necessary to understand when you're looking at this kind of work, a little bit of introduction to this research project and its context. Then we'll dive right into exactly what I was trying to figure out with this experiment. We'll talk about some of the software that I used to establish the things that I was looking for, the exact procedure that the program that I wrote actually undertook. And of course, we'll get into talking about the data and the results towards the end, which is mostly going to be in the form of figures more than any tables or specific numbers, just because there's so much of it that it's easier to summarize. And we'll wrap up with a few formalities, some acknowledgements, of course, sources, and then I'll give you my contact information at the very end in case you have any questions and you would like to talk to me about them. So, in order to understand this project, it is very much a computer science project. Everything that I've been doing is effectively computer science, but its context is biological, and that's why it's within the Department of Biology. So in order to understand the work that I'm doing, it's necessary that we talk about a couple of pretty basic biological concepts. And the first one here is the idea of cooperation. Cooperation is basically any animal behavior where one animal gives something up for another animal. And the effect of this is to, at least in the short term, is to increase the probability that the recipient reproduces by increasing its evolutionary fitness. And so this kind of poses a puzzle because anybody with a basic understanding of evolution knows that behaviors that increase the actor's fitness are generally favorable. So cooperation actually decreases the actor's fitness relative to its population because it's helping other individuals reproduce. So it's a little bit strange that that we see it in so many animals. Just for example, obviously humans are cooperative. That's the one obvious example that people go for. But in the wild, you'll see things like sharing food, for instance, or one that I really like to use is the example of musk oxen forming circles around their young, which actually puts them at more risk of injury from predators, but it does protect their young. So it increases the probability that their young are going to reproduce while decreasing their own probability of survival. So it's a little bit of a puzzle. And previous research has actually showed that the reason that cooperation is so common is that it's beneficial over repeated interactions. So over the first interaction, it might seem a little bit counterintuitive. But when individuals start to interact over and over again and begin to recognize each other and the behaviors that individuals are likely to conduct, it becomes beneficial to be a cooperator because then everybody knows that you're somebody that's likely to cooperate. And that ultimately improves the probability that you receive cooperative behaviors in return. This is going a little bit into game theory, so I'm going to kind of gloss over the rest of that. Feel free, again, to ask me questions later if you have them. Now we need to talk about the concept of social inheritance. And social inheritance is a principle that has been established by previous research as well, which basically says that most animal social networks obey a pretty simple pattern. There are three probabilities. First of all, there's a probability P sub B, which is the probability that a child forms a social connection with its parent. Then there's P sub N, which is the probability that a child forms a social connection with a neighbor of its parent, an individual whom its parent also shares a social bond with. And finally, there's P sub R, which is the probability that a child forms a social connection with any other random individual in the population. And the theory generally states that P sub B is greater than P sub N, which is also greater than P sub R. In other words, individuals in a population are more likely to form social connections to individuals that their parents have social connections with. And this has been shown to apply to a number of animal species, including our good friends, the bottlenose dolphins, which are on the slide here. So just as a brief example, I've provided this diagram to kind of help you understand how this works. Essentially, whenever an individual is born, they connect to the parent with a probability P sub B. The two individuals on the sides are connected to the parent, so that link forms with a probability P sub N. And then finally, to the other three individuals, it doesn't show the third link, it only shows the ones that are easy to draw. But to the other three individuals, the probability P sub R is applied when forming a social connection. So the question then becomes, what happens when you overlay these things on each other? And you see a couple things happen. First of all, it should be obvious that connections to cooperators are pretty much always beneficial. So in essence, the population wants to form as many connections with cooperators as possible. And that means that when cooperation is high, the probabilities that links are formed tend to go up. But when those probabilities of linkings, when the probability that individuals form social connections rises, that actually makes cooperation harder to sustain because you have to cooperate with a larger number of individuals. And so there's this kind of inverse fluctuating relationship between P sub R and cooperation. I'll get to the relevance of that later. I just wanted to make a quick note of it here. What's most important to note is that cooperation can be made dominant under specific social costs, but it's not guaranteed to be that. And we're looking for a situation where cooperation can become the dominant strategy despite whatever environmental factors may apply. Because with cooperative species, you see that regardless of their environment, they display cooperative behaviors. So that's what we're looking for here. And one thing that had been postulated was that what I've dubbed discriminatory inheritance might increase cooperation. So what is discriminatory inheritance? Basically, it's the concept of social inheritance repeated, except that P sub n, which is the probability that a newborn connects to a neighbor of its parent, is subdivided based on some information that the newborn knows about those individuals. For example, say that the dark blue individual at the bottom of the screen here is a cooperator and the light blue individual is a defector. Then the newborn gets to connect to those individuals with different probabilities based on their social strategy. That's just one example. There are other treatment groups that I used to display discriminatory inheritance as well. I'll get to that later. But that's, in essence, what I wanted to figure out here. Does this idea of discriminatory inheritance, providing the newborn individual with some information about the individuals it's connecting to, increase cooperation? And the hypothesis was that yes, it does. Because things like this that allow closely knit groups to form increase assortment. And assortment in past research has been shown to be positively correlated with cooperation. So my hypothesis ended up being that when we allow discriminatory inheritance to occur, we increase the assortment of the population, the degree to which things are interconnected in close groups, and that is going to increase cooperation. So how exactly did I go about determining all of this? Well, first we have to talk about the software that I used to write all of this. It's a programming language called Julia, which is, I believe, most functionally similar to Python. The main difference being that it's got some added functionality for handling large data sets. The text editor that I used was Atom, although that's essentially irrelevant. What's most important here to note is that I have downloaded several pre-written Julia packages to help make all of this easier. Stats-based just includes some simple statistical functions. JLD2 is going to allow quick generation of large numbers of data files. And then plots is going to take those data files and turn them into a simple graph, which I'll show you later in this presentation. So what exactly happened under this simulation is that we've got a population of 100 individuals that undergoes 100,000 generations. And in each generation, we see 100 birth-death events. A birth-death event just means that a random individual is chosen to die off, and then it is replaced by a newborn individual. And that newborn individual is going to select its parent for probability P sub B based on the evolutionary fitness of all of the other individuals. In other words, if an individual is highly fit, evolutionarily speaking, it's more likely to be a parent. And then once all of the social bonds have formed along the lines of social inheritance or discriminatory inheritance, whichever one we're using, all of the individuals in the population are going to cooperate, which in essence means that if an individual is a cooperator, it's going to pay a cost, which was set at 0.5, in order to distribute a benefit evenly among all of its social connections. And benefit was one of the variables that I changed throughout this experiment just to get a wider range of data. Another variable that I changed link, which is a cost that is additionally implemented on all individuals in the population per social connection that they have. And the reason for doing this is that it makes social connections less beneficial. So it effectively imposes a limit on cooperation so that you don't get arbitrarily high data. And then finally, of course, once all of this cooperation is done, you factor the payoffs into the evolutionary fitness as an exponent, and it all begins again. Another random individual dies, and you just restart the cycle. As far as the actual experiment is concerned, we've got 3 experimental groups, one with just basic social inheritance, which is just P sub n. Then, as I previously mentioned, there's discriminatory inheritance by strategy, which separates cooperators and defectors. And finally, and this one is a little bit more difficult to understand, there's discriminatory inheritance by familiarity, which means that if a parent inherited a certain social connection from a grandparent, then the grandchild will connect to that individual with a probability P sub ni. But if a parent randomly generated a link with probability P sub r, then the child won't do P sub I, it'll do P sub nr. This is effectively a measure of how related an individual is to the newborn. And then I did take measurements after the first 20% of generations. That's because you generally need about 20,000 generations for all of these dynamics to stabilize to a point where you can measure them without having to worry too much about variation. I took measurements of the frequency of cooperation, obviously, and also of assortment, which was in effect the difference between the actual assortment that was visualized and the assortment that we expected to see. Now, let's look at some results. This is the part everybody loves to talk about. I will say that I'm going to go fairly quickly through several charts here. Feel free to pause the video and take a look at any given one if you'd like to. This is in essence what I was looking at after each round of this experiment. So you'll see here we've got linking costs along the bottom. Linking cost is inversely related to cooperation, whereas benefit is directly related to cooperation, and we've got a range of benefit values along the side there. And so this is, for instance, the treatment group of just basic social inheritance, so just P sub n, and this is the frequency of cooperation that we saw. And so you'll see there's a pretty immediate pattern where cooperation tends to increase as benefit increases, and there's a sweet spot between high linking cost and low benefit, and low linking cost and high benefit, where cooperation is most sustainable. And so this is the kind of thing that I'm looking at on a regular basis. You see kind of a similar pattern with assortment, where there's kind of this upward stripe where it's higher, and that's where the correlation comes in between these two variables. So this is what I'm looking at, but I've taken that and now made these charts. And this is a little bit harder to interpret because obviously there's not a clear pattern. What this shows is the change in cooperation from basic social inheritance to discriminatory inheritance by strategy. And the reason that there's not a pattern is because the pattern either isn't present or is too small to be detected with the amount of variation that are present in these data. What is important to note is that almost all of these data are positive, which means that discriminatory inheritance increased the amount of cooperation versus just normal social inheritance. You'll see also that there's generally positive changes in assortment for discriminatory inheritance by strategy. You see positive changes in cooperation for discriminatory inheritance by familiarity, and positive changes in discriminatory inheritance by familiarity for assortment. So what all of that ultimately means is that there is a positive relationship between the presence of discriminatory inheritance and assortment and cooperation. So that reaffirms part of my hypothesis. The issue, though, is that there's relatively little correlation between assortment and cooperation. This was actually the highest I could get that correlation to come. It's about 0.537 for discriminatory inheritance by strategy. For the other testing group, it was even less. You see there's a positive relationship there, but it's not really the kind of thing you would say is causal. So that part of the that part of my hypothesis I generally rejected. Additionally, what was interesting to find is, again, going back to P sub B, it's generally in previous research has been fixed at 1. And the reason this is significant is because in most animal populations, it's very, very close to 1. But in this experiment, I actually allowed it to evolve, because when you fix it at 1, you actually see that cooperation is arbitrarily high, even at ridiculously high P sub R values and ridiculously high linking cost values, which, remember, we had said both of those variables are inversely related with cooperation. So that's not something we would expect to see mathematically. This is really more what we're looking for, and that's what you get when you allow P sub B to mutate from generation to generation. So, brief bit of discussion here. We conclude that assortment does not explain the increase in cooperation, and there's probably a third variable at play. So that's what I'm working on now, is looking at some other variables. Future research should specifically focus on, there's actually a dip in assortment. If we go back to this chart here, you'll see at the top of the graph, there are low assortment values, and that wasn't something that I expected to see. So that is something that I am going to look at in the future. Additionally, we've concluded that all future research should allow PISA B to mutate, because otherwise you arbitrarily increase cooperation by guaranteeing that every individual will always have a social connection. So these are some people I'd like to acknowledge. Of course, Dr. Jeremy Van Cleve, he has been a blessing throughout this process, incredibly helpful. I'd also like to thank the Kentucky Young Researchers Program for giving me this opportunity, and of course, Ms. Karen Young and the MSCC program for giving me an avenue to conduct some research before I went to college. These are my sources here. And if you do have any questions about this presentation, please feel free to email me at parker.smith@stu.fayette.kyschools.us. I've, at the moment, got nothing but time on my hands, so I'll be happy to answer any questions that I may have left you with. Thanks so much for watching, and I will see you all later.